Kia ora team, welcome to this 2012 question on static electricity. So this experiment performed by Robert Millikan in 1909 determined the size of the charge on an electron. Millikan put a charge on a tiny drop of oil and measured how strong an applied electric field had to be in order to stop the oil from falling. The diagram below shows a simplified version of the apparatus he used. Okie doke. So, the first question, question A, asks us to explain why the battery is connected as shown in the diagram. So if we look at the diagram over here, we see that this is the battery. One end of the battery has a longer line, and then the other end of the battery, which is connected to the wire, has a shorter line. So the side of the battery, which has the longer line, is the positive terminal, whereas the other side, which has the shorter line, is the negative terminal. And in class, I would have given you a little bit of a hack to tell you that if we have a long line, this long line gets broken into two pieces, and then we can make a nice plus sign with those two broken pieces of the long line. And so that's how I kind of remember which side is positive and which side is negative in our electricity diagram. So if this end of the battery is positive, it must be supplying this plate with positive charge all along here. And if this end of the battery is negative, this must be supplying this plate with negative charge over here, okay? And so the reason why the battery is connected to the plates in such a way is because this is what allows the oil droplet to be stationary, aka float in the middle of the plates. And so how does this setup allow the oil drop to float? Well, as you can see, this oil drop is negatively charged. Okay, and so by having the positive plate up top, there is going to be a force that is going to pull the oil drop upwards. What is this force called? It's the electrostatic force, because opposites attract, and that is essentially the basis or the explanation of an electrostatic force. It's when opposite charges attract. So that's why the negatively charged oil drop has an upwards electrostatic force to the positive plate. In the opposite direction, we've got gravity. Okay, so gravity is the force that would pull the oil drop down. So because these two forces are equal and opposite, okay, and because we have the top plate that is positive, this is what is essential to allow the oil drop to float or be suspended in the middle of the two plates. This is only possible with this arrangement or setup of the experiment. If we had the positive plate down low, okay, the oil drop would have a force that only pulls it downwards, and it wouldn't float as it does now. Okay, so the explanation is worth a merit, and this is what I've written. For the negatively charged oil drop to remain stationary between the two plates, the upper plate needs to be positive and the bottom plate must be negative. This is because while gravity works to pull the oil drop down, the positively charged plate will allow for an electrostatic force to pull the oil drop upwards. When both forces are equal and opposite, the negatively charged oil drop will remain stationary between the plates, and that's because of the equal pull from both directions. Okay. Next question is question B. In terms of the forces, state the conditions necessary for the oil drop to be held stationary between the horizontal plates. So we've kind of already discussed this. The answer for that is that we've got two forces in opposing directions that are equal in size. And so that is worth and achieved. The gravity force should be equal in size and opposite in the direction to the electrostatic force, which is upwards. Okay. Part C. On one occasion, Millikan used an oil drop of a mass of 2.54 times 10 to the power of negative 5 kgs. So this is the mass. With a charge of 3.6 times 10 to the power of negative 9. So this is the charge of the oil drop. The plates were 4.8 times 10 to the negative 4 meters apart. So this is the distance. Calculate the voltage needed to hold the oil drop stationary between the two plates. Start by working out the weight force of the oil drop using this equation here. Okay, so it gives us a hint. We have to use this equation here to first work out the weight force of the oil drop. So this is the first step. What we want to end up working out, or the aim of the question, is to calculate the voltage needed to hold the oil drop stationary. What is the voltage supplied by this battery for this whole thing to work? And so we're going to need to have an equation which incorporates voltage, okay? And so the equation, if you look at your formula sheet, that incorporates voltage and uses the information that the question has given us is E, which is electric field strength, equals voltage over distance, okay? In order to work out voltage, we have the distance, which is provided over here, but what we need is we need the electric field strength, okay? And with electric field strength and distance, we can rearrange this thing to find the voltage. So to find the electric field strength using another equation, have a look at your formula sheet. What do you think you will use? This is the equation that will be most sensible, okay? And so using this progression, first working out the weight force, okay? First working out the weight force. You can use the weight force, or the force worked out from here, plug it into F equals EQ, all right? And then what you can do is rearrange this equation to find E and plug it into this equation here, okay? So you kind of have to go on a little bit of a rabbit hole, find out what you have, find out what you don't have, and then use the appropriate equations to get you the answer that you need. Okay, so first things first, let's work out the weight force of the oil drop downwards. So we've got F equals the mass, which was given in the question over here, times acceleration due to gravity, which is 9.8. This gives us this value here. Now we can use this value and plug it into this force, okay, this electrostatic force equation here. The reason why we can plug our downwards force into the upwards electrostatic force is because these two are equal, remember? According to this diagram, the downwards gravitational force is equal to the upwards electrostatic force. And so that's why we can plug in this F value into this equation here, because this is the electrostatic force equation. Okay, so plugging all our values in, we've got our force, our gravitational force, which is equal to our electrostatic force plugged in here. Then we have E, which is what we're trying to figure out. And then we have our charge on the oil drop, which has been given to us here. So I've plugged that in. Now, we have to do some simple algebra to work out what the electric field strength is. So then we can plug it into this equation here. So to get E all by itself, currently it's being times by 3.6 times 10 to the power of negative 9. So I need to get rid of this. How do I get rid of something that is multiplied? Well, I have to divide by this number. So I'm going to do that, and so that cancels this out. And what I do to one side of the equal sign, I have to do to the other, so which is why I've divided this side by this value here. So what we're left with is E equals this portion over here, which I've rewritten here, okay? Plug that into your calculator. What do you get? Hopefully you've gotten this value here, okay? So this is your electric field strength. Once you have your electric field strength, then you can finally use this equation to find the voltage, okay? Because that's the aim of this whole question. So let's substitute the values that we have. We've finally worked out our electric field strength, and so I've plugged that into this E over here, equals voltage, which is unknown, over the distance between the plates, which was given to us over here. And so, time to rearrange this thing to get voltage. Currently, voltage is attached to divide 4.8 times 10 to the power of negative 4. So to get rid of divide by, we times, okay? Because the opposite of divide is times. And so by timesing both sides by 4.8 times 10 to the power of negative 4, I'm left with V equals this equation over here, okay? This part over here I've rewritten down here. So plug that into your calculator. What do you get? We've got a voltage supply of 33.189 volts. And that is what is allowing the oil drop to be suspended between the two plates. Hopefully that makes sense. That was worth an excellence, and I'll see you in the next question.